Hello once again and welcome to the third part of the lecture series, Factors Influencing Ventilation, Perfusion, Gaseous Exchange and Transport. And in this section we'll deal with gaseous exchange and arterial blood gases. So getting down to the business end of things. So the business end, it looks a bit like this. So this is a very simplistic representation. Going back to the final slide, the summary slide of lecture 2. We had the situation of ventilation perfusion matching. So we've got this similar representation of a single alveolus, and again you've got the wall of the alveolus a single cell thick, and the interface with the capillary of the pulmonary circulation with blood flowing around or coursing around the capillary beds, and again one cell thick. So very simplistically, we've got a pressure driven system which gives a net movement of oxygen into the pulmonary circulation and a movement out of the pulmonary circulation of carbon dioxide. So in the content of this lecture, we'll unpick this simple arrangement to provide an explanation of arterial blood gases. So that will lead into lecture 4, where we'll consider some of the clinical implications. So the left-hand panel of this slide provides a little bit more detailed representation of the interface between an alveolus and a capillary, pulmonary capillary. So you've got the capillary outlined in red, okay, which I'm denoting here, the cell of the nucleus of the endothelial cell, and hemoglobin within the plasma. Okay, this interface, you've got the alveolar wall here. Again, both structures, as we've mentioned already, are a single cell thick. You've got wet surfaces, interstitial fluid. So you've got an arrangement of alveolus and gas within the alveoli, the alveolar wall, interstitial space, capillary wall, plasma, hemoglobin. This arrangement is the respiratory membrane, and we've got a simple arrangement in terms of a pressure-driven system in terms of gas diffusing across the respiratory membrane within the lungs, resulting in a net movement of oxygen into the circulation because partial pressures of oxygen are higher within alveoli than returning blood to the lungs. Okay, and we've got the opposite movement of carbon dioxide. Just something for you to think about, those second and third bullet points. If you think a little bit about ventilation and perfusion matching, what factors might affect diffusion? What sort of things might affect the volume of gas in the lungs, the thickness of the membrane, etc. Thinks about density in terms of the capillary beds, maybe dehydration, and also red blood cells, erythrocyte, hemoglobin, in terms of cases of anemia, perhaps. So, all things that can further affect, as we mentioned, whether it be physiological or pathological. So this is the arrangement in terms of oxygen movement and oxygen transport. and you'll see that this will make perfect sense of arterial blood gases when we get to cover them a little bit more detail in a short period of time. So simple representation, we've got again our alveolar wall, interstitial space, capillary wall, plasma, red blood cell, hemoglobin within the plasma. Okay, so we've got a net movement of a higher pressure to a low pressure. Oxygen is driven across the alveolar wall through the interstitial space and across the capillary wall, and again dissolves into plasma. So about 1% of oxygen dissolved into plasma, but the rest, as I'm sure you're aware, probably about 95% or plus in terms of healthy subjects, combines with hemoglobin to form oxyhemoglobin. We can express this relationship in terms of partial pressures of oxygen within plasma and percentage saturation of oxygen with hemoglobin through the oxygen dissociation curve. So you've got this S-shaped curve, which I'm outlining here. Again, on the X axis across the bottom, you've got partial pressures of oxygen in millimeters of mercury. A little bit confusing. This is taken from an American text. In the UK, Europe, we tend to use kilopascals, but it's the concept that's important. So we've got increasing pressure of partial pressure of oxygen carried in with plasma related to the percentage in terms of combined with hemoglobin. So you can see high pressures, relatively high pressures of partial pressure of oxygen within the plasma. We've got fine, this picture is fine. We've got sort of 95% plus saturation of hemoglobin with oxygen. Okay. So again, we saw the previous slide, it's around in excess of 95%, but around 1-2% carried in plasma. You can see that we can get quite dramatic drops of partial pressures of oxygen in plasma, and we don't get too much change in terms of saturation, which is good news. Okay, but again, once you sort of hit below low 90s and below 90, the relationship changes. So you get relatively small changes of partial pressure here for big drops in saturations, and this is, this has implications even for prescription of supplementary oxygen with some of the people that we work with respiratory disorders. And again, probably in healthy subjects, if you think about mountaineers and supplementary oxygen required normally about 20,000 feet, because again, atmospheric pressure of oxygen drops, therefore partial pressures of oxygen drop in plasma, therefore saturations drop. People suffer from hypoxemia. Okay. So hold that thought in terms of partial pressures of oxygen and relationships with oxygen saturation. Similar picture in carbon dioxide. So if we move to the next slide, this is a summary of the picture. Similar process for carbon dioxide, so that we've got in tissue level, so metabolism producing waste products and carbon dioxide, and we get a pressure gradient of carbon dioxide into the bloodstream, and again pressure driven system, so that you get about 10% of carbon dioxide exerting a partial pressure carried in the plasma, and drivers, again pressure drivers into hemoglobin as well in terms of the carriage of carbon dioxide, either dissolved in each case, as you can see, combinations of carbon dioxide and water, which forms carbonic acid and dissociates with two bicarbonate ions and hydrogen ions. Okay, a combination just sort of dissolved or dissolved in, combined with protein in plasma, and similar pictures within hemoglobin. So the processes I've covered over the last 3 slides can be sort of pulled together in terms of arterial blood gas. And these are readings that are important for us in terms of respiratory physiotherapy. So we've got a pH value. This is normal readings, obviously. A pH value of 7.35 to 7.45. Hydrogen ion concentration in terms of 36 to 44 nanomoles per litre. Partial pressures of oxygen, 10.5 to 14 kilopascals. Remember I said that, in UK and Europe tend to use kilopascals rather than millimeters of mercury, which I've represented here in brackets. Partial pressures of carbon dioxide, normal values of 4.5 to 6 kilopascals. Bicarbonate, which we mentioned, 22 to 26 millimoles per litre. Base excess, which is a strange value, which I'll come to explain in due course, -2 to +2, and saturation levels, 95 plus. So this is a picture of normal blood gas readings, and so we'll, again, probably for those of you who've particularly studied chemistry or biology previously, this will be make sense, but for those of you who haven't or have forgotten, I make no excuse in terms of moving through each value, very slow time. So over the next few slides, we'll cover, well, John, this seems very good, but what does it mean? Okay, so again, going back to GCSE chemistry or something like that, or even before that, in terms of pH scales, again, neutral being pH 7, anything above is alkaline, anything below is an acid. Okay, so in terms of arterial blood gases, the pH, it's just a scale that represents the concentration of hydrogen ions in a solution. So again, as I've indicated at the image on the previous slide, if it becomes more acidic, the pH decreases, and if it the concentration is excreted via the kidneys, and carbon dioxide is excreted via the lungs. But again, if it's getting more alkali, it raises, and hence we got a normal range, slightly alkali picture, 7.35 to 7.45. Partial pressure of oxygen in plasma, as we've mentioned, this is part of your continuum of movement on a microscopic level in terms of a pressure driven system, but only a very small amount, between 1 and 3 or 2 to 3% I've represented there, but very small amount combined with plasma. The rest is carried attached to hemoglobin in red blood cells. Okay, so partial pressure of oxygen. Partial pressure of carbon dioxide, similarly, it's the partial pressure of the carbon dioxide contained within plasma. And again, we've got the summary in terms of bullet points, in terms of the chemical reactions, in terms of combinations of water to form carbonic acid, which then dissociates to bicarbonate and hydrogen ions. Okay, and a repeat of the normal range there. Bicarbonate ions, basically it acts as a buffer, and it's one of the mechanisms used to try and maintain normal pHs. I won't go into it very deeply on the next presentation, but your body will always try and compensate for ill health. So again, as we'll see later on in the program, bicarbonate ion concentration is quite one of the factors which indicates possible compensation. And again, the last two slides have mentioned the kidneys. Again, arterial blood gas derangement can be caused by respiratory problems, as is obvious. This is the point of the four lectures, but also it can be of metabolic origin. Again, it can be due to influence of things like kidney failure, etc. The base excess, as I mentioned when we were going through the arterial blood gases, it doesn't have any units, and it's just an indication of the amount of strong acid or strong alkali to be added to a solution to return to a normal pH. Okay, it's as simple as it gets. Okay, within the blood gas picture. And oxygen saturations, again 95% plus, 97% within this slide of oxygen is carried bound to hemoglobin. Okay, so there's think about normal ranges, as I said, in excess of 95%, and this can be assessed quite quickly with simple pieces of equipment. You don't need to take blood and work out arterial blood gas readings, or send it to the lab to work out arterial blood gas readings. We can get immediate feedback on saturations through pieces of equipment such as pulse oximeters. Okay, so almost there in the sunshine. It's the downward run-in to the finish for this series of lectures, and I'll meet you again for the fourth and final installment of factors influencing ventilation, perfusion, gaseous exchange and transport, where we'll consider some of the clinical implications. Thank you.